Good afternoon, I'm Mr. Ish. Thank you for joining me. Let's formalize this topic a bit more, this concept on infinite geometric series. We've already done an introduction on this. Let's formalize it. Ideally, you want to use the word series versus sequence, but many students use the word series and sequence or sequences interchangeably. Technically, series is the better term, infinite geometric series. Imagine you are evaluating something which looks like this. N equals 0 up to infinity. We have 1 over 2 to the power of n. This will be a geometric series developing as you put these nth terms 0, 1, 2 all the way up to infinity. You know some of the terms that will develop is 1 over 2 to the 0, 1 over 2 to the 1, 1 over 2 square, and then 1 over 2 cube onwards all the way up to 1 over 2 to the infinity. But what you're doing here is not just simply itemizing them, you're adding them up, you're determining their sum. And there's a common ratio that is to be seen over here. Take any of these two terms, 1 and the one right before, and you'll find a common ratio. Take this 1 over 4 and 1 over 2, you'll do 1 over 4 divided by 1 over 2, and you'll get a 1 over 2. Take 1 over 8 divided by 1 over 4, you'll always have a common ratio of 1 over 2. We know the formula in all instances for anything which is like this, n equals 0 or n equals any number here, but up to infinity, Sn is always, as you remember, a, which is your first term, a1 over 1 minus r. But what exactly is my first term over here? It would be this right here, the first term. The formula would be 1 over, and now 1 minus r, which is 1 over 2. You'll have 1 over 1 over 2, and you'll see a value here develop of 2. If you were to add all of these, 1 over 2 to the power 0, which is just a 1 plus half plus quarter plus 1/8 all the way, you'll get a value 2. Initially you make big gains, but as his denominator gets increasingly large, geometrically large, exponentially large, as you can say in terms of this power, the gains are so minuscule that they add up in very finite small amounts, so you still end up with a finite value here of 2, and you end up seeing convergence. You have to remember this formula over here applies to infinite geometric series of these sorts. You don't want to make the mistake of handling this in terms of an integral question. For the sake of a argument here, what would happen if you had treated this as a integral question, thinking that we can easily graph this as a function? Imagine this was your function 1 over 2 to the power of x, and there, it doesn't matter what letter you use, and you could graph it. Then you try to do the area below the curve, because if you were to give each number in your series a width of 1, you could give it a length of whatever that function was, and you could think that you can just add these up and get an area of the curve. The area of the curve would be equal to the sums, but you would find out that that type of reasoning does not work over here. If I'm using variable here n, I can do dn, it doesn't matter, and then you would have to integrate this and see what would happen when you integrate this. You'll have to use the substitution rule or the u substitution rule, the polynomial substitution, because you're looking at everything like this, 2 to the power of minus n dn. You've brought this up. You can do u is equal to minus n, then you can do du is equal to minus dn, dn is equal to minus du, but you have to bring in a new set of limits because this is definite integral. u1, u2, you'd put everything here with regards to this. It would be 0, and here you'd have minus infinity. When you bring in these substitutions, everything, this is how it will play out. You'll have 0, minus infinity, this minus du, you can bring the minus here, 2 to the power of u du. You can use a property of intervals and integrals where you can bring the minus and flip these out, because you want to have a larger number and a smaller number here. Here you have the reverse, smaller number on the top, upper limit, and a larger number here in the lower limit. By bringing this minus, you can flip everything around, so you're looking at minus infinity 0, 2 to the power of u du. When you integrate this, you have 2 to the power of u over ln2. Remember the integral of 2 to the power of x, or anything to the power of x. A power function is always something like this. You would have everything here from 0 up to minus infinity. Do not resubstitute the u because you're doing a definite integral. If you resubstitute the u, then you must go back to your original limits. You'll do here 1 over ln2 times 2 to the power of 0 minus 2 to the power of minus infinity. 2 to the power of minus infinity is like 1 over 2 to the infinity, which will zero out. You will end up seeing over here 1 over natural log 2. And now compare these two end results. The integration is giving me this as the sum, which is really not the sum. You're basically just calculating the area below the curve. You're getting 1 divided by 2 natural log. You're getting 1.44. That 1.44 is wrong. the limit of this specific series, infinite geometric series, is 2 and not this. So do not treat this as a integral question. It's not an integral question of this style that you're familiar with. Compare this to what I'm going to put for you right over here. N is equal to 1 and infinity 1 over 2 to the power of n. Again, it's the same item over here. The ratio will still be the same, 1 over 2, but now look at what this value here is. The sum of these infinite numbers in this geometric series S infinity is going to be this your a divided by 1 minus r. What's the a over here? It'll be 1 over 2 to the power of 1 will be your first term, then you'll go on from there. Your first term is a 1 over 2. You'll have 1 over 2 divided by 1 minus 1 over 2. You'll have 1 over 2 divided by 1 over 2, and here your value here is a 1. Why is there such a big difference here in terms of the sum of all of these series in this particular example versus the one previously 2? Why is there such a big difference? It's not seemingly a big difference, but by means of series or sum of infinite geometric series, this is a big jump. It's a big difference. The reason is right over here, n equals 1 and n equals 0. By going here from n equals 0, in excluding that number out, you will really be excluding 1 over 2 to the power 0. You're excluding a 1 plus. This entire 1 is being excluded from your series in terms of the total sum. When you look over here, this specific series, your first number ends up being 1 over 2. So your sums start from 1 over 2. Here your sums start with, you have this big jump here simply because you did n equals 0. You have a smaller jump here in terms of the total sum because here you're doing n equals 1. Hence you see this big difference play out. And again, do not treat this as an integral question. If you treated this as an integral question here, from 1 to infinity, 1 over 2 to the n, dn, you can do the exact same steps as I did for the previous integral question. You would, in this instance, you would get a value here, 1 over 2 ln 2 as the area below the curve, but this area below the curve will not be representative of the sum of these numbers in this infinite geometric series. So you have to pay particular attention to that. Treat these exactly as you see them. Do not treat them as an integral question. But that's it for this video right here. Thank you for watching.